Good afternoon, guys. Welcome back into my channel. So in this lecture and lab configuration, we're going to talk about spanning tree. So STP spanning tree protocol, it's automatically remove layer 2 switch loops by shutting down the redundant legs. A redundant leg is an additional leg between two switches. Say a redundant leg is usually created for backup purposes. Just like every coin has two sides. A redundant leg along with several advantages has some disadvantage too as well. The biggest disadvantage of a redundant leg it is that it creates a loop between switches. If a loop exists, two switches, they do not work properly. So in this tutorial, guys, we're going to talk about the layer 2 switches loop, cost, solution, and the first part of this tutorial is followed. So what is STP? STP is a protocol. It actively monitors all link of the network to find a redundant link. It uses an algorithm known as the STP, known as the STA, which is spanning tree algorithm. The STA algorithm first creates a topology database, then it finds a disable the redundant leg. Once redundant leg are disabled, only the STP chosen leg remain active. If a new leg is added on an existing leg is removed, the STP will run the STP algorithm and we adjust all legs 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 to reflect the change. Now, so BPDU, which is Bridge Protocol Data Unit or Multicast Frame, which switches use to share information about themselves and their connections. Besides sharing information, switches also use BPDUs to learn the network topology, to learn which switch is connected with which switches, and to learn whether any layer 2 switches loop exists in the learning topology or not. So wood bridge. A wood bridge is a starting point of the STP network topology. To elect a wood bridge from all switches of the network, STP use two parameters, a variable known as bridge priority and the MAC address of participating switches. A switch that has the lowest bridge priority value is selected as the wood bridge. If the bridge primary value is the same in all switches, the switch which has the lowest MAC address is selected as the wood bridge. By default, the bridge priority value is set to 32768 in all Cisco switches. Unless you change this value, a switch has the lowest MAC address is selected as the wood bridge. If you want a specific switch to be elected as the root bridge, you can set the bridge priority value of that switch to less than 32,668. The selection process of the root bridge explained each time when a network change occurs, like a new switch is added in the network topology, or an existing switch is removed, or the current bridge is filled. If other switches of the network do not receive BPDUs from the root bridge within 20 seconds, they assume that the root bridge has failed. If the current bridge is failed, remaining switches automatically start the election process to choose the new root bridge again. Now, the non-root bridge, except the root bridge, all remaining switches of the network are considered as the non-root bridge. Non-root bridges receive update from the root bridge and update their STP database relatively. So port cost. Based on the connected media link, the STP assign a value to each port of the network. This value is known as the port cost value. STP use this value to choose the single best path when multiple links are available between two switches. It selects the port which has the lowest port cost value. So now, guys, there go a table. So there are two sets of the port cost value. They have bandwidth is 10 gigabit per second. Old cost value is 1. The new is 1. So you could follow along with these, just seeing. So there go the path cost. So we're not trying to make this video long, but it's very important for you to understand the very concept of STP before you go ahead and start, a lab with STP. So path cost is an accumulated value of the port cost from the root bridge to other switches in the network. It is also calculated from the root bridge. Default path cost of the root bridge is 0. BPDU contain the path cost information. When the root bridge advertises BPDU out from its NFS, it sets the path cost to 0. So you can see here they have the root port, they have the designated port, they have the non-designated port, they have the STP port states, and STP blocking state. So you need to understand all these: STP listening state and STP learning states. So STP forwarding states. So these are all the things that you have to learn, not just only learn how to configure and observe STP topology, but then you need to understand what is STP or what is its purpose, what is it done. STP operational in nutshell. So it says all switches of the STP domain first elect a root bridge. This root bridge acts as a point of reference for all other switches in the network. All parts of the root bridge remain in the forwarding mode. So all of that. Now, before I jump into the lab today, let's talk a little bit more about the access distribution and core layers. Let's explain them. So the term campus LAN refers to a LAN network that spans a single geographic location, such as a building or university campus, a campus LAN, whatever. Now, let's say that the Cisco Layer 3 hierarchical model is a set of recommendation that describe how a campus land network should be designed. This model suggests that instead of designing a flat campus land network, an administrator should design a hierarchical campus land network. A hierarchical network is easier to manage and troubleshoot than a flat network. So said the Cisco three-layer hierarchical model contain three layers: core, distribution, and access. So the core layer is the backbone. That's what a core layer is. It's the backbone of the network. It provides a high-speed connection between different distribution layer devices. The distribution layer connected the access layer to the core layer, and the access layer provides initial connection to end user. So if you want to, you could come, just take your time and study this and get to know them and understand them. So the access layer, it says the access layer is the first layer of the Cisco three-layer hierarchical model. This layer allows an end user to access the network. This layer also connected user device such as PCs, IP, phone, wireless, access point, pointers, scanners to the network. So bang, 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 you can take your time and just go over this and understand them. So this is a topology. So this is west of the LAN, connected to the device, west of the LAN, connected to the device. So the distribution layer is the second layer of the Cisco three layers hierarchical model. Switches connected in this layer are known as distribution switches. Unlike the access switches, distribution switches do not provide any service to end devices. So distribution switches connected to access switches. Now it says access layer, distribution layer, and then building 1 and building 2. So go ahead and talk about the core layer. So this is the third layer of the Cisco three-layer hierarchical model. Switches that work in this layer are known as the core switches. Core switches connected distribution switches. If a complex and a large network, core switches reduce cabling needs and switch port while still allowing all devices to send data to all other devices in the LAN. So guys, I was, preparing this lecture before I jump into the lab for CCMP and Core V8 version 8 to observe STP topology change. So I hope this was being helpful. So again, it's always important for you to understand the concept of something before you go jump and start making a configuration. So I hope this was very helpful. Um, oh, oh God, um, I closed this by mistake. So let's go ahead and reopen this and start this lab. No. Okay. Okay, so let's go ahead and open that. Yeah, I don't know where it's at, so let's just replace it. Okay. Let's make this goes here. Let's open this, make this bigger. Let's grab the other one. It's the instruction. Okay, guys, so let's carry this over. I feel like this is too big, so make this a little bit smaller. Okay. All right. So guys, first thing first, the STP protocol, how it operates. We're going to use this topology here. What we're going to do in this activity first, we're going to first observe the topology, and then we are going to do some scenarios here. We're gonna see all the flows and all the paths. So let's check out this topology here, guys. We have the access layer, and we have all the nodes. So the access layer switch connected to the distribution layer. And then we have what? So how to use redundancies between switches and see them in some cases. One of them links gets broken, the second one can still operate. So then on this surface is still existing as on the access to an end user. Okay, so say that we have this connection between the access layer and the distribution. So each layer has two connections. One of the connection is working. It says probably if we can distinguish this. So we have the green light, and then we get the second one. Say for instance, the second one is broken. So here in this entire color, so we could say that like say switch, says this switch 6 is connected to the distribution core, and this is the only redundancy when this switch will be broken or fall out or stop working, and the second one will still get the surface, and still both of them will going to be in the green. So in this scenario, let's say if we have, you know, so which of these are connected to the distribution layer and through D2, so we can distinguish this by both of them have the green light, but it's block all the STP by the distribution layer. Yeah. So we have four switches here on D2, D1, D2, D3, and D4. So they all are connected to the core layer. And C2, because of both of them are in green, so now it's not working. So in this topology, we are now going to work in this activity, going to ping from PCA to from PC1 to PC6. So the two devices, of course, are going to also observe the IPR to begin. So, so say in this here, it says to check the STP convergence, right? So to it says to observe the STP convergence. So let's go ahead and let's go ahead. So Pulse simulator. So with this simulator, what we're going to do is, so we're gonna hit packet data unit from PC1 to PC6, right? Then we're going to use this. So you can see the BPDU, we should have the ICMP messages. So this would, find out the MAC address of the destination device, which is PC6. So, here's step one. So you could see that A1 is selected the path to D2 because, as I mentioned, this is now the card working, but as you can see, both of them are green, and the one is idle, so it's blocked by the STP, and this is the part that we're going to use, where it's which path that the first one, that I say C2, and the first one. So this one is not working. Just a second. So as you can see here, this is the broadcast. So here, this is the broadcast because of the ARP, but now we're talking about the core layer. Oh, sorry. Uh, sorry guys. Okay, so you see, so So now you can see, sorry. So now we could have an ARP broadcast because of ARP protocol. So, so now PC1 have the MAC address of PC6. So the ICMP is going to work as you can see here. So there was a question to follow the path to A1, D2, D3, PC6. So let's see. So as you can see, I go all the path, and as we observe it, so now guys, we're going to a different scenario one, as it says. So we have done this path. So it says, second. So we already done this. So it says examine the ARP process again below. So it says click here to create new scenario one. So let's go in scenario. Let's make this one. And then so it says in scenario one. So it says in scenario one, Okay, so it's PC4 to PC5. Start simulation. Now the ICMP started. So now we got a broadcast. So now this is not working because STP is blocking this link and this too as well. Everything you see the yellow line, this is where the STP is blocking it. Now it says to test the redundancy. It says to test the redundancy in a switch network. So this here, we're going to delete this link. So from A1 to D2, now you can see if you get a ping from now let's delete. I said on step 3 it says to delete link between C1 and D3. Oh, it's C1 and D3. So which is this. So let's press this. So C1 and escape. Now let's see. Let's see and see. So let's see what are the other steps. It says we have to ping from PC1 to C, from PC1 to PC3. So let's say we grab this PC1 to PC6. So let's see the path from, the most important is the path from PC1 to PC6. So I apologize for this lab. It's kind of annoying on with packet tracer. So it's kind of take time because it's frozen every now and again. You got a clear event and see. Okay, so now it says bang it from there. Now it says that in step 7 we have to delete C1. So let's say delete. Gotta delete. Oh, that was scenario 2, and this is scenario 3. So it says we gotta delete this switch. And switch, skip. Then let's do. And now we are going to ping from PC1 to PC6 and see. So you see all the path here, guys. So one thing here, guys, we should delete the 4 as well. So let's go ahead and see. Skip. Now let's see. Let's check this out. It says that ping from PC1 to PC6. So that's the last step. Yeah. So I apologize for a little delay for the convergence to be established. So you see all the path from PC1 to PC6. So thank you so very much. I appreciate you guys will follow along with me. Stay tuned for more interesting lab with the CCNP Anchor. Thank you.